Quantum amplitude estimation and numerical integration. We will be doing this in Google Colab. Like we did in previous video, we will start with installation of BlueCat. We can do it by using this code !pip install BlueCat. Type the code that was shown earlier in Google Colab. Then click on play button and BlueCat will be installed. Quantum amplitude estimation and numerical integration is a specific application of quantum amplitude estimation as numerical integration calculations. First of all, numerical integration is an integral calculation done numerically by a computer. The integral interval is divided into a finite number of subintervals to approximate the function to be integrated. The integral value can be calculated numerically as the sum of the areas of the subintervals. The integral value obtained by this method is only an approximation, and the accuracy of the approximation is determined by how finely the interval is divided. In contrast, the definite integral taught in school is an analytic integral, which is different from numerical integration. For example, a function such as f(x) equals x squared can be integrated analytically by hand calculation as follows. Analytical integration is superior to numerical integration in that it does not introduce approximation errors, but numerical integration is also often used because it is difficult to perform analytical integration calculations for complex functions. Quantum amplitude estimation is known to accelerate this numerical integration to the second power compared to classical computation. To find the integral of a function f(x), we prepare the following state. I equals O 2 exponential n-1 is the representative point within each subinterval in the Riemann sum. Are the auxiliary qubits used to label each state. Here we estimate the amplitude of the state that is. Calculating the amplitude of, we get. This is exactly the same as the calculation of the Riemann sum. Therefore, we need a quantum gate that prepares the state as above. In the following example, we have corresponding to f(x) equals sin square x. This example can be implemented very efficiently using the properties of RY gates. Now let's import the code. Let's implement. The following is a 3-qubit circuit, where the qubit $Q_0 is an auxiliary qubit for labels. Using this circuit, let's check that. First, we act the H-gates on Q1 and Q2 to create a superposition state of 00 wrangle, 01 wrangle, 10 wrangle, 11 wrangle. Next, with Q1 and Q2 as the control qubits, act the RY gate on Q0 changing the rotation angle. The probability of measuring Q0 equals 1, PR, Q0 equals 1, is as follows. Next, for f(x) equals sin square x, divide the interval, 0, pi by 4, into 4 parts and set the representative point to be the midpoint of each interval, x1, equals, pi, by 32, 3 pi, by 32, 5 pi, by 32, 7 pi, by 32. The Riemann sum is as follows. We can see that it is equal to PR, Q0 equals 1, except for the coefficient, pi, by 4, which represents the integral interval. From the above, we can see that the numerical integration results can be obtained by finding PR, Q0 equals 1, by quantum amplitude estimation. The point here is that the superposition of Q1 and Q2, 00 wrangle, 01 wrangle, 10 wrangle, 11 wrangle, is used to perform the calculation for the 4 representative points, x1, at once. If more qubits are used, the numerical integration can be divided into more subintervals, increasing the approximation accuracy. The following is implementation of amplitude using BlueCat. with a probability close to 0.1796. 1 is measured on the auxiliary qubit. Next, we prepare the oracle to be used for amplitude estimation. It is the same as the oracle for amplitude amplification. Verify that amplitude amplification is achieved using these oracles. The probability of measuring 1 has been amplified and it's okay. In the original quantum amplitude estimation, the amplitude was estimated by performing quantum phase estimation with the oracle. However, quantum phase estimation requires a large number of auxiliary qubits as the accuracy increases, which increases the scale of the quantum circuit. Therefore, in recent years, several methods have been proposed that do not use quantum phase estimation. One of them is to maximize the following likelihood function L, H, theta. Sin square theta is the probability of getting 1 on the measurement of the auxiliary qubit. M_k, k equals 0, 1. M is the number of times the oracle will act on the prepared state. After acting the oracle M_k times for each k, n shots measurements is performed on the auxiliary qubit. H_k is the number of times that 1 is measured for each k. If we can find theta, that maximizes the likelihood function above, we can get the amplitude we want to estimate as sin theta. In the following, we implement a method using the maximum likelihood estimation described above. We will carry on the following two estimation methods. Amplitude estimation using maximum likelihood estimation. Amplitude estimation by direct multiple sampling for state psi wrangle equals amplitude 0 wrangle. Repeat the amplitude estimation 100 times, keeping the number of sampling constant. Let's check the accuracy of the estimation with the squared value of the amplitude using the obtained 100 times results. It can be confirmed that the method using maximum likelihood estimation is able to estimate the data with less variance. In summary, we were able to perform numerical integration by quantum amplitude estimation without quantum phase estimation. In maximum likelihood estimation, we need to take into account the amount of computation required to maximize the likelihood function and the existence of local maxima. In the implementation example above, if the number of obtunas trials n_trials is reduced, the maximum likelihood estimation gets stuck in the local solution and the estimation accuracy deteriorates significantly. That's all for today. Thank you.